Okay, so I want to welcome you again and thank Stefano. Rodolfo, I'm out of it today. Rodolfo and Marcel for this discussion. This is a technique that I've always wanted to know more about and really don't know anything about. So I'm looking forward to hearing about the gravitational iconel.
Okay, thanks. So yeah, the goal is to make this session as informal as possible. So please feel free to stop with comments or questions anytime. So Marcel and I decided kind of to organize it in two parts. I'll try just to give a short 15 minutes general introduction to the idea of gravitational iconal. So if you want in one line, gravitational iconal is the idea to start from some microscopic quantum calculation and then go in a regime where quantum numbers like the energy or the mass of the object become large. And then you want to extract from this microscopic calculation the classical contribution, right? So the intuition is that when quantum numbers become large, you get some classical contribution. And you can do it in several ways. And in these techniques of the iconal, you do it through an exponentiation. Right? You'll see that there are terms that have become leading in this large energy, large mass limit, and they will conspire to exponentiate. And what is at the exponent, that's the classical contribution. So that's in one line, the idea. And this has been a subject that has been investigated for decades in the context also of string theory. So we're trying a bit to give follow the historical idea. Most of this idea came from the study of asymptotically flat case, right? And then around 2006, 2005, people started also thinking about very concretely about the same problem in asymptotically ADS. So I think there are ideas that motivations, goals that one can learn from what's going on in the asymptotically flat case that have not been explored yet in the asymptotically ADS, in the holography setup. And so the first part is mainly focusing on this asymptotically flat story, try to give some ideas, and then Marcel will do most of the discussion on the ADS part, saying what has been done and yeah, trying to highlight what has not been done. Very good. Okay, so I should do this. Okay, so let me start with some motivation coming from the microstate, story before going to the flat space. So the main idea is how to extract dynamical information from microstates, right? So in the IPHT framework, we have very concrete observables that we can calculate. And the first ones that people focused on are kind of three-point function. So you have your heavy state describing conceptually a microstate of black hole, or as far as you can get. And then you want to see a one-point function in the heavy state coming in and coming out. So from the geometric point of view, these are related to multiples, right? So how the back reaction of the heavy state in the geometry decays at the asymptotically ADS part, right? And we have heard also in the conference that this can be made very precise, and there is precision holography. So there is a very nice story there. But the idea is to go beyond that and to try to probe the heavy state more dynamically, right? So, okay, what you can do is just to do one step further and study 4-point correlator, right? So you have your heavy state coming in as a cat, your heavy state as a bra, and then you see, you insert two light states. So you can think about this 4-point function as a response. So you can think about one of these light state as a non-normalizable perturbation at the ADS boundary. And then you want to see the response of this non-normalizable perturbation in another point at the boundary. So we are not thinking about the subtleties of coincident points. Let's not do that. And that response is basically this 4-point correlation. There is actually a lot of dynamical information hidden here. You can think about this response as kind of tidal perturbation, right? So you kick your system and then you want to see how it responds. And you can also see this, and there's been like 20 years discussion, this observable as a clean kind of a very concrete setup to study information loss, right? So you, in that case, you want to see what is the late time behavior. So you do some, you insert some perturbation at 0 time, and then what happens at very, very, very late time. So calculating this 4-point correlator is very hard to do it exactly. So you, and also depends on how precisely you want to define that. So if you kind of the first thing you can do is to say, okay, let me model the heavy state just as a black hole. And then, for instance, in this late time behavior story, you would expect just an exponential decay if the black hole has some temperature. And that's kind of lost because you throw something in and nothing comes out. But you would expect different result, as we had from Imin talk, about if you do it the same calculation in a statistical ensemble, and we would also expect even more different result if you do it in a pure state. But as I said, it's difficult to calculate this correlator, so the idea is to try and tackle the problem some simplified setup. And you can either look at some more tractable observables, so easier things that still capture the interesting physics, but are not the full 4-point correlator. And I understand, and for instance, these form factors, I mean, this thing that Imin was talking about, they could be a good observable to look at. Or you can stick to the 4-point function and try to calculate in some approximation. And the idea here is to use this classical approximation. So this is the general setup. And I also would like to motivate that it would be very interesting to go beyond this case and study the full heavy correlator, where you have the interaction between, instead of a microstate and a probe, of 2 different microstates, right? And this is even more complicated setup. Okay.
Isn't
Yeah.
even known how to do that?
Yeah, okay, exactly, of course not. But again, you can do some perturbation theory. I would like to motivate what perturbative approach you can do and why it would be interesting. Yeah. So exactly, in order to do this, let me do a step back and go to asymptotically flat space. The idea is the following, right? So let me set it up in the simplest possible setup. Think about modeling the heavy state as just a minimally coupled scalar to gravity. So this is kind of an IPHT approach where you put as little information as possible about the heavy state, just saying that it has some mass and the coupling that you have to have, right? The minimal coupling. And let me think about this case, heavy prime. And so you have one scalar with some mass m1 and some scalar with some mass m2. Now, the idea of the perturbation theory I had in mind, answering Nick's point, is instead of considering a head-on collision, which would be very hard, think about a collision with a large impact parameter, right? So it's a collision with a lot of center of mass energy, but large impact parameter B. And you want to calculate what happens. And you expect what happens, you would expect a deflection, right? So the 2 things come in and they deflect. Now, this deflection is a classical observable. So this is something that happens classically. And the question is, how can you derive that information from a quantum calculation, right? So in this setup, the microscopic calculation is just doing Feynman graph, Feynman amplitude, where you have gravitons interacting with this massive object. So the idea is that this bending is the effect of the exchange of a large number of very soft gravitons between these two objects. And so if you calculate just an naive perturbation theory with one exchange, you are badly off, right? So what you should do is consider diagrams with an increasing number of exchange gravitons and resum them. And the idea is, okay, you don't need to resum the whole diagram. It would be very hard to calculate a diagram with the n+1 exchange graviton. That's an n-loop diagram, right? But from that diagram, you want to take the leading contribution when the mass, the center of mass energy is large, and you want to resum that leading contribution. And you can prove in this case, just yeah, you can really prove that this leading order calculation resums to an exponential. And that exponential here, that's what we call Iconal. Right? So, and now what I want to explain is why this is the leading icon. So let me just summarize briefly what I said. In an IPHT approach, you model black hole as massive scalar, minimally coupled. And you do an expansion parameter, the expansion perturbation theory is an expansion in this parameter, where these are all not classical quantities. So R is related to the mass of the object or the energy of the object. And you see, we take the typical scaling of a black hole of microstates, right? So the mass is large, G is small, Gm is fixed, and B, the impact parameter is very large. Now, once you have this leading iconal, what you can do, well, the idea is that from there you can derive all the classical quantities. So for instance, this deflection angle that I mentioned is the derivative of the iconal with respect to the impact parameter. Right? So that's a gauge invariant. So you don't need to worry about coordinates, right? It's not. It's a fully gauge invariant quantity that depends just on the in data and is something observable. You can also, for instance, look at the time delay. So if you want the difference between the time that an object would take in empty space and the time it would take after gravitational interaction is taken into account, that time delay is basically related to the derivative of the icon with respect to the energy. So you have all these quantities. Now, the leading iconal here just captures the leading term in the large mass limit of these diagrams with many gravitons. The subleading terms hide extra new classical contribution. So the idea is that every time you add one graviton, you have contribution that contribute to the exponentiation of this, and then new contribution that gives new term that themselves will get exponentiated. So what happens is that this object in the exponent, in this large impact parameter expansion, right, in this expansion here, is itself an expansion in R over B, right? And the leading iconal is the case k equals 0. Yeah, I think, sorry, here I have a mistake. I think I should have this, the deflection angle. The leading iconal basically is, yeah, goes like G, the subleading iconal goes like G squared, the sub-subleading iconal goes like G cube, and so on and so forth. Very good. So this is the general idea. Now let me just have two quick slides saying why this problem has been investigated very thoroughly in the last 4 or 5 years. Yeah, maybe even 3-4 years. And the reason is that even if this is a scattering problem, there is a nice link to the bound problem, right? So the bound problem is this one. And people are interested because this is experimentally relevant, right? So instead of having two very massive objects scattering, you have they are bound. And in GR, what happens is that they emit gravitational waves, so they lower the energy, and then they spiral very slowly till a certain point. There is a violent part of the process where there is the merger, and then you have a single object forming, which rings down to the equilibrium, right? So this is experimentally, this is taken from the first paper of the LIGO-Virgo collaboration. And you see they are very open-minded because these are the black holes. And at the horizon, which is this gray area here, GR would predict just flat space, empty space, but they picture some blobs or some possible. So this is just to say that, okay, there is no resolution to say whether from the current data, whether at the horizon scale you have stuff or not, right? And here it gives you some interesting scales. You see the black thing is exactly this parameter, is R over B. And you see that in the inspiral part, it goes, so this is the inverse, B over R, right? So this is B in unit of R, and you see that it goes down, right? So when you discuss the inspiral part, this large impact parameter story is relevant. Now you say, okay, there is still a difference. This is a bound problem, and this was a scattering problem. But a few years ago, I think this paper kind of motivated the study of the scattering problem to extract relevant information from the bound problem, said that this can be done. And you see, it just the abstract ends with a challenge, right, to people doing QFT. Please do calculate diagrams such as this one, because from diagrams such as this one, we can understand what type of gravitational interaction two objects have, right? And then use that information to study bound problem in that effective metric. So the logic is the following: you do a scattering problem, and that amplitude story takes into account all the non-complicated non-linearity of gravity. So these two particle to body system is not as easy as Newton, right? So you take into account that. Then you ask, what would be an effective metric that would give the same scattering angle, the same quantity that you calculate from diagrams in just a one-body problem? Like you want to find an effective one-body problem. And this is what Thibaut Damour and collaborator did back in the 1999. Now, once you have that effective one-body problem, you fix the data of that effective one-body problem, you can very well study bound orbit in that effective one-body. And that's very popular, and is what is done in practice to give information and generate, is one of the techniques used to generate these templates, which are necessary then to compare with data and to find C. Okay, so I almost finished my part. I just want to say what are the challenges that this flat space analysis showed, and that might be interesting to study in the asymptotic LRDS. So the general idea, the general lesson that people extracted. Oh, and by the way, I have no references here because they would be too long to write references. If you are interested in any kind of where this was done, just please let me know, and then I'm happy to discuss.
Can I ask a question? Yeah. You said that you use the scattering data to construct an effective single body problem.
Yeah.
And then it sounds like a miracle, but you're saying that the single body problem bound state gives you exact correct information about the bound state of the original problem. Yeah. Why should that be? I don't know.
Yeah, I don't know. I mean, I don't find it that surprising, because these scattering geodesics, they probe distances that are relevant for the bound object, right? So they get close enough. It's just they have too much energy to be bound, right? But they probe the interesting. Okay, here I don't have the figure, but think about this bending, right? So where most of the action goes on, that's the same kind of distances that are relevant for this in-spiral phase, right? So if you learn how the gravitational field behave there, then you can say, okay, let me just have an effective description of that, and then just lower the energy, right? You fix the parameter of this effective description, and then you say, okay, any problem is any process in that effective description comes. Yeah.
So my main thought is, if you have the scattering problem, these are kind of like ultra relativistic particles.
Not necessarily. Very good. Yeah, that's a good point, right? So and this is something, okay, we're also discussing with Marcel, and so you see, for the classical limit, you require that this object is large, right? But it can be large in different ways, right? It can be large because the mass is large. It can be large because the energy is large, right? The only thing you really need for iconalization, for extracting this classical contribution, is that the iconal becomes large and it gets exponentiated, right? So this result that I'm not writing at all, but people have been discussing these deltas here. You should think about them as function of B, the impact parameter, function of the kinetic energy of the object, right? So basically, if you want the relative boost gamma of the two objects, and that's a function that is kept exact in this process, and you can do small v, large v, right? You can interpolate. So this expansion is usually called post-mean constant, right? If you are interested in the bound problem, then you want to take this parameter r over b of the same order as the velocity, because it's bound, right? The kinetic energy is the same order of the potential energy. And so you want to do also a small velocity limit, right? So you would take what is usually goes under the name of post-Newtonian, right? But this captures terms that are relevant to fix this effect in one body, and then you can fit this effect in one body. And
my misconception, I think, was I was thinking this is an ultra-relativistic process at which point it only probes the sort of conformal class of the metric and not. Yeah.
It's interesting also to study the ultra-relativistic because you want to see, is it consistent? I mean, this is something that we did in collaboration with Paolo Di Vecchia, Gabriele and Carlo Heisenberg. So that we were thinking a lot about this high energy limit. It gives you consistency checks, but it's more of a conceptual thing than applying to this. Okay, so what I want to say is that this setup has general masses M1 and M2. So it's more like heavy prime is a black hole binary, right? You can think that one of the two is much larger than the other, right? And then at that point, this iconal should be, if you do that limit, so the very asymmetric limit, this iconal should go back to the heavy light case, right? So the iconal should capture just the geodesics of the light object, the object with the smaller mass in the background of the heavy object, right? So that prob limit is interesting. And it just so happens that the first two terms of the iconal are completely determined by the prob limit. It's not obvious, right? And okay, people did first the hard calculation, right? And then we did also the hard calculation in general dimension, right? And then after, people realized that you can start from the geodesics, and it's not obvious in particular for delta 1 for the 2 p.m. And then for the scalar case, you can just derive everything from the prob limit. So in some sense, yeah, please.
Is that also true for idea?
That's a good question. I don't know.
What was the question?
So whether this fact that the prob limit determines the heavy prime is true also for RDS. Yeah, I don't know. I don't know. I basically know nothing about the heavy prime in RDS. That's one of the message of this one. So what I want to say is that in the flat space case, delta 2 is the first interesting heavy prime object, and that's why here is called. There is the mention of two-loop scattering. So that data, please.
So I'm confused. So the first leading order radiation is delta 2, which is the third box.
Yeah, exactly. Yeah, I'm coming to that.
Okay, I was going to ask, is there a relation with the post-Newtonian way of thinking of the radiation? Because there also enters at 2.5.
Yeah. Yes.
Not an exact. There's not an exact mapping. But this is supposed to be possible.
No, I can comment. Yeah. Let me just.
And this is just a base question. So this is calculation the shape because you are heavy operator.
Okay, here I'm doing flat space. So there is no CFT, there is no holography. You have to wait Marcel for the holography. is just saying that it's this conceptually is the same problem. So the idea is we would like to tackle the same problem in a holographic setup, where you cut off, you do the coupling limit, you cut off the flat space, and then you say, okay, I have now, instead of Feynman diagram, I calculate Witten diagrams, I calculate correlators. Can I extract a gravitational iconal? And how does that gravitational iconal?
Yeah, the reason why I ask is like a Shefty or even ADS, the scattering is I don't know.
Yes, yes, exactly. So instead of the scattering, instead of this diagram, you would have CFT correlator. Right? So this is calculated with Feynman diagram. That's the microscopic thing from which you want to extract the gravitational iconal to exponentiation. And in CFT, that calculation will be substituted by this calculation. And if you are in the regime where one mass is much smaller than the other, then you can do this simpler calculation. Very good. So let me come to the radiation problem. So yeah, so when you look at delta 2 is third order in the Newton constant, as Daniel was saying. Many things happen, and it would be nice to understand the same problem in ADS. So one thing is that this delta 2 develops an imaginary part, right? So you have e to the 2I delta, right? And delta develops an imaginary part. So basically, the elastic process describing just two things come in and the same two things come out is exponentially suppressed, right? Because I times I is minus, right? That imaginary part will be positive. So the elastic process is suppressed. So what's going on? Well, what's going on is that gravity, instead of just deflecting object, wants to do more, deflect the object and produce a lot of radiation. So the dominant diagram, the dominant contribution would be something like that, right? Two things come out, they deflect. Two things come in, they deflect, come out, and there is a lot of graviton, a lot of radiation. So this is what people, a lot of people, also including here in Saclay, are studying, right? How to include radiation, because that's definitely that's the thing we detect, right? That's the gravitational group. And the second thing that happens, and it's related, is that the problem limit is not enough, right? In order to really to calculate the deflection angles, or even the part that relates not to radiation, the parts that relates to the massive object, you need some hard calculation, right? And diagrams is one way of doing that. Now let me come to the post-Minkowski post-Newtonian. So in some sense, post-Minkowskian is harder, but it contains post-Newtonian as a subset, right? So all the results in post-Minkowskian are written in terms of an arbitrary relative velocity between the two objects, and nothing stops you just to take and expand that velocity around zero, and you have a double expansion, right? And at that point, you recover the result of post-Newtonian. So if you do this for radiation, right? So you will calculate this time, and you do the post-Newtonian, you'll indeed find that the first contribution is at 2.5 pm. Now, the advantage of post-Newtonian is that since you do a double expansion, it's you can push it to higher order. So in some sense, kind of people from post-Minkowskian used post-Newtonian data to check that they are correct, and they provide the further data that then post-Newtonian people can see whether they match, right? Because you can expand the velocity. Very good. So let me do just the cartoon. So if we come to this question, if you want to do ADS, okay, heavy would look like something like this, and heavy, light would look something like that, right? So, and the ingredient now, the microscopic ingredient is the correlator instead of Feynman diagram. And there has been a lot of activity also in this ADS, but mainly on this part of the heavy, light, right? And so why? Let me conclude just saying what are the motivations. Then Marcel will say more. So one motivation, at least for me, to consider the RDS case is that now you have an extra scale, you have RDS, right? So you can play a bit more. You don't have, in the flat space case, we were doing always this large impact parameter story. Now you can also take another approximation. I don't know, the mass of the black hole much smaller than the RDS scale, right? Put the black hole very much inside, or the microstate very much inside the RDS3 cap. And then the question is, you can go both ways. You can use geometries and bulk calculation to derive CFT quantities, right? So you can derive anomalous dimension and things like that. And Marcel maybe will say something more about that. Or you can do the other way around. You can say, okay, can we use CFT constraints? And the bootstrap constraints is one of the key to say whether geometries are allowed or not. Right. So one of our original motivation was, let's take a singular geometry and calculate the iconal, give an interpretation in terms of CFT of this iconal. Does it provide consistent CFT data or not? Right. And I think for the future, something which is very interesting would be to go back, look at this heavy story, and then import all the lessons from flat space, look at radiation and things like that. Okay, sorry, I took much more time than I wanted, so let me stop here. And maybe Marcel, go on, and then there are questions. Yeah.
Stupid question. I remember eons ago there were these papers of Microstate and Strominger where they looked at the moduli space of BNPV black holes. Literally, I don't think they were scattering at high speed, but they tried to enumerate the moduli space. So that looks a lot like this sort of heavy scattering. This is not. This doesn't have it doesn't seem to fit quite in this.
It's not because it's actually moderately earthly and people.
Okay, but still, the question is, can you get in really? Can you take these old results about the moduli space of BNPV black holes and perhaps extract some of this data from them in an interesting way?
Yeah.
The picture just reminded me of this old story, and it's kind of trivial because it's not trivial, but there's no kinetics involved because, or very little kinetics because the moduli space is, they sit there, they're BNPV, so the multi-center. Oh, anyway.
So we were showing that radiation starts at 3 p.m.
Yeah.
And we do these impressive runs at 2 p.m. But the scanning angle is still finite. We spent I assume not like to go to 4 p.m. even in the real part.
Yeah.
And how would you address that without using proximal?
Yes. So the short answer is I don't know. I mean, this is a very interesting question. It's something people are thinking and debating right now. So let me maybe just say briefly, unpack the question. So I was saying here that delta 2 is the first place where kind of this new physics come out, right? Come into the game related to radiation. Now, is there anything even more new at delta 3, right? So that would be the 4 p.m. in this language, so G to the 4th. So as I was saying here, that's not complete, so it's a work in progress. So people are, various groups are trying to kind of, are computing, right, this thing in adding different pieces, right? Now the question is, when you have, if I understand correctly, when you have the whole answer, is this whole answer for the 4 p.m. completely well defined at all scales, at all energies, right? So you, it's just something that you can have a PN expansion, you can have a high energy expansion, right? It will just tell you that there is a finite deflection angle, a finite time delay, and correction to the energy emitted, to the gravitational wave.
Because I wonder about, usually when you have higher divergences, you have to look at cross sections or inclusive quantities. Instead, you look at 2 to 2, And it seems like sort of an accident that it shows up the divergence only in the imaginary part that doesn't happen.
Yeah,
So
yeah.
how would the spread the bootstrap?
Yeah. So
the technique.
What type of divergence are you thinking? Infrared divergences or ultra relativistic divergences?
No, the IR.
The IR.
Yeah.
So 1 over epsilon. I thought that we can maybe discuss offline, but I thought that the IR divergences have been cancelled for already with the contribution that people calculated so far at 4 p.m. And what is left are high energy divergences, which, maybe you can think about them as also IR, because high energy is like a small mass. I mean, in this parameter, in this boost parameter, gamma is like E over M. So those divergences are still there, right, at 4 p.m. This, I think, is still open problem to see whether you get a well-defined deflection angle at all energies. But the recent result in December by the group of Zwibern and Porto, I think they canceled all the 1 over epsilon divergences at 4 p.m.
You're mentioning sort of the energy scales and that it might not be valid everywhere. So like where is it not valid? Is it I mean, can I think of like for emeries, is this okay when the one mass is much bigger than the other, or what's the energy scale?
Yeah, so this problem is a conceptual one. It's nothing to do with the with this setup.
Yeah.
Because in this setup, the kinetic energy is always smaller than the potential energy. You are in a bound, right? So the total energy is negative, right? But you could think about a scattering process, and maybe they will be detected, right? I don't know. People also think about that, right? Just transient phenomena where you have maybe primordial black hole scattering, right? So we don't have any evidence of experimental evidence, but it's something you can consider. And then if you consider that process, in that case, you can have as much kinetic energy as you want. Now, the question is this PM expansion, which is large impact parameter, if I fix the impact parameter in some sense, is it valid really to all energy, right? Can I take the gamma relativistic factor, relative relativistic factor as large as I can, right? Now, of course, what happens is that you start emitting more and more energy, right? And then you might run into problem. You emit more energy that you had before. You see that the angle diverges, right? So you might see some strange thing. And this does not happen at 3 p.m. But yeah, people don't know whether there is a problem at 4 p.m. or higher.
I mean, I guess conceptually, you could also think of it as maybe as for fixed impact parameters, you keep increasing the energy. At some point, they'll want to form a big horizon together or something, and it'll be effectively like they're colliding head on.
Yeah, okay, we can discuss that more, but we increase the energy by keeping this R fixed. So you see that's what I'm saying. The Schwarzschild radius is G over M, but if you are at very high energy, it's actually G over E, right? So you do a limit where you still have object with some radius, and then the question is whether you are left with some factor of energy that is not hidden in this R, and then that could. I mean, there is a lot of interest development, even kind of numerical relativity people. Franz Pretorius is interested in this high energy limit. And I don't know, one question that you may ask, which is relevant for fastball, is that I think the intuition from GR is that in this very high energy limit, I mean, the slogan I have is that matter does not matter, right? So that it's not relevant what is the black hole, right? If it's a scalar or something, right? So you're not relevant to M or the strike. You're just probing pure GR, right? Okay, that would be a big kind of intention with fastball, right? Where we always say that, okay, the string theory, fast is relevant. So yeah, this high energy is more conceptual, and the bound system is more relevant for experiment. Yeah, please, yes. Yeah.
How much time do I have?
You know, how long was a piece of string with this?
Okay,
No,
good.
but
Let's find out.
No, but more seriously, over a half hour. You know.
Yeah, that should be fun. Okay, great. Okay, so as Rodolfo said, I'm sort of gonna take a side to the step to the side and talk about this, the ADS part of this story, which is much more recent and not as well developed. Where did the slide end? Okay. Yeah, so from the bulk point of view, we can also study the same or similar problem in ADS. And so we have some geometry in the center and we probe it with some light probe. Now I'm going to take all of the special cases that Rodolfo mentioned. So I'm going to take this, effectively this ultra relativistic type case. I'm going to, so then the mass of the probe kind of gets washed out from the physics. And I kind of just do the simplest things first, because if you're starting from scratch in the ADS case, then you do the simplest cases first. So from the bulk point of view, this same delta, the notation is the same. This iconal phase. Now, I should say all of these geometries and pictures that I have in mind for this talk are in 3D. And if we consider microstate geometries, then we're only going to consider ones that have a consistent reduction to an ADS3 type geometry. And here we also assume that we have the relevant killing vectors in these two directions. So we can similarly define some stationary phase type quantity, some delta, some iconal in this way. And here this delta t is this time delay, and we have some angular shift. So the idea is that this can be trivially done in empty ADS, and some difference occurs when we fill the inside with some massive object, be it some classical black hole, some conical defect, some microstate geometry. And the difference in behaviors of this quantity between the two different cases tells us interesting.
So when you say time delay, it's the time delay between what two times? One
Yeah.
launch to
On the boundary, you start, you launch into the center, it interacts, we don't know quite what happens, it comes out at the boundary somewhere else, we collect that data and we compare the two. Okay. And so this quantity, like in the flat space case, depends on the initial data that you put in, these conserved momenta. In our conventions, PT is negative, just as a warning in case someone always asks that, but slightly weird conventions. Okay. So from the bulk point of view, at least with the caveats of me taking all of these simplifying limits that Rodolfo mentioned as a first case, from the bulk point of view, this quantity is a very simple calculation right there, relatively. You have to do integrals, but you are just computing integrals. So even though this is the probe limit, it turns out that it contains a lot of information. Maybe it's not surprising after Rodolfo's introduction, but also because we're in ADS and we're in this particular setup, we have quite a lot to say about and from the CFT. In particular, as was kind of introduced in the CFT, in the ADS context, in the probe limit, correlators of this type, where you have two heavy and two light operators, are what you should study, and information about these correlators is contained within this delta. And what this means is, although you might maybe first guess that this delta contains information about the heavy object in the center, actually it knows a lot more than that, and it knows a lot about what I'm going to schematically write in CFD kind of notation. It knows about the bound states. It knows about the excited spectrum on top of the microstates. So I guess the first question when you're starting a new idea like this is, what is the dictionary? How is information coded? It's likely to be complicated until you know the math. Okay, here I had motivations, but really these are the same. These are kind of motivations that Rodolfo already mentioned. So does this very simple quantity distinguish between, I mean, if you've never calculated one, it's maybe the first question. Even from the bulk point of view, is it in this probe limit and taking away simplifying assumptions, is it enough to tell the difference between singular geometries and so really what you have in the bulk? Okay, this is ends up to be yes, quite simply. And then can it also tell between microstates? If I have some family of microstates, can it tell between the different members of the ensemble? Okay, it's just good to check how much, how fine-grained the information that this thing can extract. And then, as Rodolfo mentioned, maybe once you map all these questions to the CFT, maybe you can use the heavy machinery that we have in 2D CFT. In this case, it's 2D CFT, where we have lots of constraints from symmetry, like crossing, et cetera, and maybe there's some fundamental difference between the information, the CFT information that's extracted from more singular geometries, where I have in mind stuff like this, and from microstate geometries. It's sort of a biased question and motivation from our point of view, but okay, maybe. Purely in the are these methods, is this quantity sufficiently knowledgeable, sufficiently fine-grained in order to study some of the more black hole regime physics of particularly scaling microstate geometries? Can it really probe deep in the geometry? So anyway, so those are kind of motivations. So let me just start from the very basics. Details are going to be lacking, and references again are going to be lacking, but yeah, just ask if you want to know where something was done. Yeah, so as I said, you start with some CFT correlator of this form where you have two heavy, two light operators. The light operators are, we have in mind some probe. And the notation, the language just means this different scaling of the dimensions of these operators. So as Rodolfo mentioned, we have in the ADS story these two different dimensionless parameters that we can expand in, and therefore we can play a bit more. So one useful one in this context is what I'm going to be calling mu, and it's just a convenient, it's like GM in ADS radius units in the bulk, and it's sort of, roughly speaking, the dimension of the heavy operator over central charge, because the heavy operator scales like C. So this is fixed in this large central charge limit, and we're going to study it with using it as a tool, as an expansion parameter. Okay, by now everyone in the room knows that we actually have access to some of these correlators, at least in the supergravity large N limit. So I don't need to talk too much about those. But it's it seems obvious for us, but in most contexts we don't have access to these explicit correlators with explicit, precise, heavy, heavy operators in them. We don't need to make some very simplifying assumptions like reducing a full correlation function down to a one Virasoro block or something like this, which is kind of what you have to do if you don't have access to what we have access to in the setup. Okay, so what can we do with this correlator? Well, we're in 2D CFT, or CFT in general, and we can look at the crossing symmetries of this correlator. And we can precisely study two different channels of this correlator, what I just call the direct channel and the cross channel. Okay, in this talk, precise details are not important. This is an expansion in global conformal blocks, which are here, and they depend on which channel you are talking about. Now, maybe just one thing to note, or two things to note, let's say. You have the CFT data of the operators exchanged, the primaries exchanged in this correlation function. You have the CFT data here in three-point functions and also in anomalous dimensions or dimensions, which are of the exchange operator, which are inside of the blocks. And you have these two different channels, and in general, and definitely in this case, the set of operators, the set of primaries exchanged in the two different channels, completely different. So let me focus on the cross channel, what we have here. So this is where you have, sorry, language is where in the cross channel for this case, the heavy operator and the light operators are fusing. And here, this is where in the intermediate channels, in the intermediate channel, we're gonna have access to information about these bound state type operators. So the dominant contribution of exchange operators in this channel are of this schematic form. It's I mean, these are often called double trace operators or double twist operators if you're in higher dimensions or whatever. In this case, it's and this is a schematic notation because you need to arrange a derivative such that you have some primary. But it's a 2-parameter family labeled by M and N bar. And these M and N bars are going to show up in essentially everything. So these have some conformal dimensions like this, where this is kind of obvious, and then you have some anomalous dimension, which are, in this case, in the heavy scaling limit, these are corrections in this expansion parameter mu. If we were in a light case, this would be like 1/n corrections. So yeah, that's what I said here. And yeah, and these in this probe limit, these are quite interesting because these give you access to information about binding energies of these bound states. Now, just studying crossing completely generically is extremely hard. There's a whole program of kind of analytic bootstrap type techniques. One interesting way that you can, people try and take different limits. You can look at, of course, your Euclidean OPE expansions and all that kind of stuff. You can look at maybe more interesting stuff, which is like Lycone OPE expansions. You're sort of having easier access to different parts of the spectrum. Another example, which is relevant for the gravitational setup that we have here, is the Regge limit. And this is a highly Lorentzian configuration. And it's very different from the other limits in the sense that you require first some analytic continuation. You already have an analytic continuation in the sense that we're treating Z and Z bar as independent quantities this is away from Euclidean. But here we then take one of these and analytically continue them. Z and Z bar, sorry, are the usual cost ratios on 2D. And then you take some limit together on the second. These correlation functions usually have branch cuts, and it's usually on the second sheet. So you have access to a completely different part of the spectrum. In the direct channel, the dominant contributions are about, it's this kind of universal contributions in the Regge limit that people like to talk about, where you have dominant contributions in the stress tensor, but also you have light double trace operators as well. And there's an interesting story behind that, but for us, more interesting right now is the cross channel, where we have fusion of heavy and light operators. And there you have dominant contribution in the Regge limit of these operators, but I'm going to have a large thin. Or in particular, in general, I have the dominant contribution from operators with large M and N bar. Okay, so kind of this equation in the box, the details are not too important and they're pretty approximate, but this is the general sort of iconal message that you have some correlation function, or in a flat space story, some amplitude, and to some approximation, you can approximate this in some limits by sort of a classical and exponentiated phase. And this, everything here that's wrapped up in this calligraphic eye, this is kind of like the, well, in the CFT story, this is the mu equals 0, like the non-interacting part of the correlator. It's the free, well, generalized free theory information that gets wrapped up into here. And so all of the interesting, in this case, mu-dependent interactions, anomalous dimensions, that kind of thing, are wrapped up in this phase. So it's sort of morally kind of similar to the flat space story. And along with this comes some dictionary between the bulk momenta and these M and N bar, which were labeling your double trace, heavy light double trace operators. In order to derive this, okay, you need a fresh pen and some paper, but so I haven't written it. But morally speaking, it's kind of what you expected. And from this, you can access by comparing, for instance, by taking your correlation function, expanding it in the cross channel, looking at studying very carefully the Reggie limit as stated here, and you can then start to map bulk quantities, which are on the right-hand side, to interesting CFD data, which will be on the left-hand side. So it's sort of visually acceptable to take this for granted, that you can relate bulk and CFD quantities. To do it, it takes a bit of work. But so let's use this mu expansion parameter. So we take use it as an expansion parameter. So this is really saying that our heavy operator, it scales with C, it scales with N, but sort of parametrically smaller. So let's do that because it's the simplest thing first. So this iconal phase admits an expansion in mu. And then we can try and solve this crossing perturbatively in mu. And there we can start to map the CFD data. Like here we have anomalous dimensions. In brackets, this is the order in mu at which this is generated. We map green quantities which are CFD and red quantities which are bulk. And similarly for 3-point functions, the same kind of story. Now, yeah, these were found in like 2018, 2019 by a group in Dublin. And interestingly, also this first order mu relation, this dictionary, is the same relation that you have in the fully light case, where you study correlation functions with 4 light operators. You study a similar Regiized dynamics, and there's a similar story at leading order in 1 over n. And interestingly, this is you get the same leading order.
Delta, the deltas from the GDs, it's usually fairly large numbers, aren't they? Because they affect the domain in time.
Yeah, right.
So not these enormous dimensions and largish numbers. Is something hidden in delta 1 I'm supposed to think about delta naught as being subtracted?
Yes.
From the GDs,
yes.
data,
No, it's a good point. I wasn't clear. Here on this right-hand side with this bulk information, this iconal phase, this is the difference. So if I go back to this bulk picture here, so this is the difference between what you get by having some heavy object in the center and what you would get if you had nothing, just black ADS. So it's the difference, which means that in terms of this expansion parameter mu, this phase starts at first order in mu.
I think he was asking about the M and M bar dependence.
Yeah.
In video, you can show one.
Okay, so
But the answer is yes, it would be.
I normally expect to mention sort of small shifts away from some integer spectrum or something, but you were telling me these are huge numbers.
Well, huge.
Well, they're
They
small
scale with M and M bar. I mean, you'll see maybe we
Yeah, I will give some explicit examples and you can see the functional form. But of course,
okay, what I'm thinking of is, an ADS, which is the return time, but then you put some heavy, superstructure on the bottom, and then it spends a hell of a long time doing this.
right. But here we're doing a mu expansion. And that's the key.
Okay, good.
No, but this mu expansion means that for small mu, it means that I have my delta heavy parametrically smaller than C. And we also have in mind, I mean, there is a kind of large impact parameter limit. So this perturbative in mu story, which was kind of the original story, which I've spoken about before here. Yeah, you're not accessing really, at least the first orders, you're not accessing the black hole type regime of scaling microstate geometry. But it's, we've got to start somewhere, huh? Okay, so yeah, these are relatively simple relations, but things get out of hand really quickly, as happens if you ever try to sit down and solve crossing relations analytically. But it turns out that this is all obviously statements in the Reggie limits, but it turns out that you can find some reasonably closed form-ish expression for the anomalous dimensions of the heavy light double trace operators in the Reggie limit. So this on the left-hand side is now exact in mu. It's not perturbative like these results. So and also this delta is exact in mu. This is just exactly what you would get from those bulk integrals at the beginning. And similarly for the 3-point functions. So we can use this as a tool. So this is now our dictionary. Basically, these relations along with identifications of quantities. So let's test it out and try and answer some of the motivating questions we had at the beginning. So for instance, let's consider a two-charge system. I don't want to do any calculations explicitly, but so let me consider the sort of singular geometry first. Let me consider the conical defect. Now for integer k, okay, we have an understanding of a dual heavy operator, but what people usually consider when they consider these geometries is the analytic continuation of k. So that's what we're going to consider. And people before us had already considered this iconal problem in exactly this geometry, without any knowledge of fuzzballs, of course. So I can find there is a precise relation that tells you how to parameterize mu in terms of the particular parameters in your given metric. But in this particular case, yeah, you can replace k by some function of mu. And you just compute some easy bulk integrals and you get some bulk information. Okay, nice. It's just what we were saying. You have some defect in the center. You send a probe in, you get some difference from empty ADS. Empty ADS would just be straight across, basically. Okay, so on the CFT side now, let's test what we just learned in generality. So we do actually, in this case, have access to one of these heavy light 4-point functions. And of course, because they were computed with some specific heavy operator, this is for integer k originally. And this integer k in the CFT is very natural because these heavy operators are built from many copies of a k-wound light operator. And so k being integer is unsurprising. Okay, but we need to try and match to this previous slide. So let's analytically continue in k. And the interpretation is not sort of exact or clear, but we have in mind that it's now describing some correlator in an ensemble of states. And here, this was just the dimension 1/2, 1/2 tower primary that we're pretty familiar with, that was used in this calculation. Okay, I don't want to write any formulae, but you can compute an exacting mu anomalous dimension for these heavy light double trace operators, and you can consider this, you can access this in two different ways. You can either solve crossing just purely internally in the CFT and access these anomalous dimensions, or you can use the dictionary we had before and compute it as a prediction from the bulk icona. And in this particular case, we find precise matching in the Regge limit. Of course, this is leading order in the Regge limit. So what does this tell us? It tells us that one of our initial hopes, in the sense of ruling out singular geometries or having the CFT observing that the CFT might have some bias about singular versus microstate type geometries, doesn't seem to play out yet, because these are solutions really to crossing. So the CFT doesn't mind these at all. This is clearly, obviously, a statement only in these probe limits, blah, blah, blah. Maybe it's not a fine-grained enough question. So now let me study the microstate geometries. Let me just take these 100 superstructure. I can do explicitly the same thing in the bulk, the same setup. I calculate some iconal. I get something very different. So already this simple bulk quantity can definitely tell the difference between, for instance, in this case, the conical defect and microstate geometries. And we also have access to the relevant heavy light correlators, thanks to Rodolfo, I guess. And we know, not in a closed form, but at least exactly in mu, and so you have access to all of the playground you want. And with some effort, you can at least get closed form expressions perturbatively in mu. Now, we do the same thing again. We solve crossing. We also get predictions with the holographic dictionary from the iconal, and in both cases, you get the same perturbatively in mu. You get the same anomalous dimension, which is given as a perturbative expansion here. So again, this is a solution to crossing, but it's a completely different solution that you obtained from the canonical defect story. And so both from the bulk and the CFT, you have a completely different results from the microstates versus the defect. So it looks like there is, at least in some sense, fine-grained enough information captured with these, which what is in the bulk, very simple quantity. So that's what I just summarized here. So maybe if we're interested in a three charge and I now consider a BTZ solution, is there something we can say here? I mean, this is a different setup, it's a different system. One immediate observation that you have is that you can't make the bulk setup for BTZ because any null geodesics that you have, we're in the ultra-relativistic case, so we're considering null geodesics of first order in the bulk. They just, this is a Nate's artistic impression. All those geodesics fall in. So there's no turning point, no solution to the turning point equations for those geodesics, and there's nothing to say. But as I guess everyone here knows, is that we also have a whole family of scaling microstate geometries that kind of asymptote, in a sense, to BTZ. So let me consider this nice family, which has useful properties that we're going to have to use in terms of killing vectors, in terms of separability, blah, blah, blah. So here I can extract, in this case of this family, I can extract a reduced three-dimensional, consistent reduced three-dimensional metric. Doesn't really matter. Everyone's probably sick of looking at this metric. But let me use it as a playground. So, okay, because actually already even the bulk, simple bulk stuff gets a bit out of hand, let me just take n equals 1. At least it's three charge. Here is the result for the iconal. This is exact in mu. I unfortunately made a mistake. I've written this in terms of alpha. Alpha is like 1 minus mu. This is just telling me which family. Oh yeah, sorry, it looks like a mess. You have elliptic integrals, but also the mess is much worse if you look at it in detail. But it's not important. It's just sort of to say that there seems to be a bit of a limit of how complicated the microstate geometries can be before you start running out of analytic power. But anyway, we can, in this case of n equal 1, still try and learn some things. So I mean, I should say, in this case of n equals 1, we also have, at least to leading order mu, the relevant heavy light correlator. And so you can study a similar problem that I described in the two-charge case. Now, we're already pretty confident this dictionary, this whole technology works. So matching things at, for instance, leading order mu, which is what you could do with the correlators that we have, it's not that surprising, maybe not that interesting. Why we're studying this a three-charge example is because really we want to see if we can scale closer to the black hole regime, which would be mu to 1, which is the opposite regime. Or, unfortunately, in the parameter that I wrote this in terms of its alpha to 0, which is mu to 1. So, okay, yes, again, we check consistency, we check everything works. At first order in mu, you solve the crossing equations, first order in perturbation theory, and you get a solution to crossing, and it's the same prediction you get from the bulk. But like I said, there's something else to consider. So let me consider this alpha to 0 or mu to 1 limit. So if I look at it from the bulk side, I look at this simple quantity, this iconal, we see that this diverges as alpha goes to 0. Now, in a sense, this is just a statement that of BTZ, that it doesn't become a well-defined quantity. But the interesting observation, oh, sorry, I just should say that, but we can go arbitrarily close, figuratively speaking, with this family of microstate geometries. And it's, the iconal is finite all the way up to this limit, this precise limit. But the interesting observation is from the CFT point of view, the solution to crossing and also the CFT data that's obtained using the dictionary is always regular and doesn't care too much about this limit. I mean, the result changes, but it doesn't blow up or something weird doesn't happen. So it's just an interesting observation that clearly the CFT doesn't mind you looking in this direction. Okay, so better to just have discussion. So I've just kind of pointed out and listed some random results and some comparisons, and it's kind of to motivate some questions in future directions. But it's basically what Rodolfo said, is that there are many extensions to this, because really for this ADS story, the CFD picture that we had, we've really taken all the simplest limits, so all the most simplifying limits. So we've washed out all information about the mass of the probe. We've actually, in what I showed, we considered the most sort of coarse-grained Reggie type limit. But as Rodolfo said, there are many ways to have a consistent classical type limit. You don't just have to take, you don't just have to, you have to have, in the CFT language, you would have to have some combination of m plus m bar to be very large. If you include masses, it would be some m plus m bar plus dimension of the light operator. And there are many ways in this combination can be large. And so these lead to many different directions of extension, which is kind of what Rodolfo said. Moving away from this probe limit, so you can maybe study this more observationally relevant setup. The radiation, I mean, you can kind of have in mind maybe it's some 5-point function with 3 light operators and 2 heavy. This is some direction to look at. And what I ended with was black hole regime type scaling, generalizations of parallel probes, blah, blah, blah. So yeah, anyway, I leave it there.
So just ask, so what might you conclude about the BTZ limit? I mean, does that mean the technique's breaking down, or as I get arbitrarily high redshift?
Well, quite the opposite, right?
Okay, so
the CFD is always, data is always regular. That's the observation.
The Eikenwald is diverging, so that doesn't.
Which is expected, because in the BTZ case, you have no well-defined problem.
Okay, but I thought the Eikenwald was supposed to give you, maybe I misunderstood, but the Eikenwald was supposed to give you some information about that. Right?
Yeah, this singular gives you this.
Oh, that, I see, okay.
I mean, okay, in all cases, you can either solve crossing, which is the hard way, or you can get it.
Oh, you can get it from there.
Sorry, all these comments are in the Reggie limit. So you can solve crossing in the Reggie limit, or you can solve crossing, or you can use the dictionary, the holographic dictionary we had, which was this.
Okay, so I've got a very dumb question.
Yeah.
The thing that you're using to get the information is diverging. So why doesn't that cause you problems in calculating this gamma?
To go from this to this, you take the dictionary that we had.
Right.
Let's see here,
Yeah.
and you resum this in the alpha to 0 limit. So
I think there is kind of exchange of limit.
right.
So
Sorry. Yeah.
if you do the limit on each term of the sum,
Yep.
you got infinity, right?
Right, exactly.
But I think what he's doing is keep alpha as a regulator, then plug in that formula.
Fantastic.
Some,
Okay. No,
and
I
then
didn't take that on board. I thought, okay, there seems to be a mismatch, but no.
Yeah, it's sort of an interesting observation that actually, from the CFT point of view, these divergences, or nothing weird seems to happen. But at the moment, it's really just an observation. It's not anything that's been worked out. It's a motivation as well.
So, yes.
So maybe to follow on this, essentially, so there's some 1,0 superscatter which are like, very deep, and they're actually too deep. They're momentum, for example, it's not quantized, it's not 1, but like 1/4 or something, which is not physical. In the CFT, the dual state doesn't care. I mean, there's a coefficient in an exponent which happens to be, which can be taken to 0 smoothly. Do you see anything in the limit? Do you see anything that says that some superstars are better than the others? There's some geometry that respond as angular momentum, and some others which don't. I have quantized angular momentum. There's anything which you can see that distinguishes between them? I mean, all this z parameter is a continuous parameter. There's nothing discrete in the.
So I think it's similar question to what we have for the conical defect, right? If we tried to answer this with the conical defect where you had this K, and the question was, does the CFT distinguish between integer K, where you would have like an intuition of just having a specific state, and not integer K, where we have some kind of, and it doesn't seem to work, at least not in this limit, right?
Yeah, I mean, this, I mean, this, Marcel was saying, I mean, this classical observable does seem to be, does seem to give well-defined CFT data, whatever this K is, right?
Yeah. Remember, he was getting the result from the black hole, where he was getting an infinitely long throw, and he was getting a finite sensible answer to the CFT. So, even if you're far too deep to be a real state, it seems like you still get decent data from that.
Yeah.
Even though it is sort of a weird thing that this works, because this kind of results, these are expanded and taking alpha to 1. And then you rewrite it, you find that, okay, this holds, and then you think, okay, now can I go the opposite way? So all of these is a kind of like, you go, the first result, like a gamma 1 and delta 1, and the one there are all expansion in mu is equal to 0 or alpha is equal to 0, right? And then you resum them, you find this formula, and then you say, can you work it out in the opposite limit? And perhaps, perhaps it doesn't work. Perhaps you're not allowed to do that, given that there's something divergent. But at the moment, we didn't find anything wrong, right?
Yeah, like you said, for one, with the conical defect case, one motivation was to see whether there was, from the CFT point of, from the sort of the dictionary point of view, the data point of view, there was some difference between what you observe for integer K and non-integer K. We have some bias between the two, so we didn't, at least in this least fine-grained setup that we have created.
Comment first. The comment is, I mean, this mystery that the new expansion that you submit, we're going to separate new equals 0. I mean, since that is just on the definition. So to know that it's structure new, you're done. There's no mystery. Would be this the question. You know, expansion in a region, you want to separate in another region. So you need to know the structure. That's it. So that will be the question. This is the comment. Second the question is probably, is there in a story you can tell scattering shock waves in ADS? That's the question. That,
sorry, could you repeat that?
Shock waves,
Yeah.
ADS, and send a probe particle, scatter. There, I know that there are story about the technology in that case. Is there something similar you can do here? The logic that you can try to distinguish is actually a shock wave or some finer information that you can extract by consistency.
Yeah. So maybe let me just if I understand the question. So that's the end. That's the problem people started looking first at. This paper that Marcel wrote, a series of papers by Cornell, Benedones, Costa, Miguel, because they were very much inspired by the ACV setup, so that's the kind of the flat space story, and they wanted to report in the RDS. So it was really kind of light scattering at very high energy, right? And that would be what Marcel was referring to as a point as the full light correlator. And the large
not be very heavy. Yeah, I mean, if you boost a big black hole, it looks like a shock.
Yeah, but if you want that, the heaviness comes from the kinetic energy, not from the bare dimension, not from the mass. Right? In this setup, it's the large boost, right? It's like the ACV, and this is what they did. And here the kind of is taking the same approach and do it in the case where one of the object is very massive, but it's not. So it's a fixed target situation, right? So one of the objects is very massive, and the other can have a large kinetic energy, right? But the kinetic energy of the second object is much smaller than the Newton constant, so does not backreact. right? So that's what but the shockwave story, I think, is more closely related to this series of paper of cost.
And from there is no.
And I think they just look at the leading icon up there, right? So in some sense, I think the message of this equation here is that here you can, the geometry is easier because you have a heavy object, you know what the back reaction should be, and can you start resumming the subleading iconals? And that sum there is that's the subleading icon in the prob limit. That makes sense.
Yeah, from this shockwave story, this more like story, that leading order in 1 over n, the dictionary looks the same.
But I don't think in that story, I don't know, maybe I don't think in that story there is a formula such as this one, right?
No.
Where you can try to, yeah.
Similar story.
No.
Yeah, no.
So initially, in this ADS story, the heavy case came second, and even though it looks slightly simpler in some ways, and so initially in the heavy story, people were kind of assuming or kind of thinking about this mu expansion, that the relationship, the holographic relationship here would be the same as what you saw at leading order in 1 over n. So, but at each order of mu, but it didn't work out. You end up with something completely different, much more information.
Probably we should break at this point and show if those are interested to talk about distant sectors about midday, and then we'll everybody meet out here at 12:40 for lunch. Well, I don't need too much later because the food, as I say, starts getting sketchy about 1 o'clock.
Okay.
So let's we can talk more after lunch, but let's just resume talking.
Okay, so then
12 o'clock and then 12:40 out here. Yeah, lunch. Okay, thank you.